Well, today we came very close to fulfilling my semester-long goal of lecturing to an empty room. Looks like we fell just one short. One way or another, today's lecture is probably going to be short anyway. It's just enough material that I feel like it needs its own lecture, but not really enough material to fulfill a full lecture. But one way or another, and I recognize the absurdity of saying this when there's one person in the room, and I know most of you probably won't watch this until probably quite a bit later, but I guess I'll put this in an email as well. Today's lecture is basically the last lecture of sort of the core material in the class. The last 2 weeks of the semester, I'm basically just going to be going over random topics that I think are useful for people to know about, but not really stuff that I have enough time to cover in the depth they deserve. So I'll just be going over a couple other topics very quickly so that you know about these methods. If you ever need them in the future, you at least know what questions to ask. The corollary to this is, since it's just sort of a grab bag of topics that I'm going over too quickly, if there's anything in particular that you're interested in, let me know and I can try to prepare a lecture on it if it's not in the slides already. Last year, for example, there were some toxicology students who wanted some information about nonlinear curve fitting to calculate LD50 curves, so I created that. I may give that lecture again if the toxicology students in the class are interested, or if there's anything else, like in the survey at the beginning of the semester, I had a couple requests to just talk about ROC curves, so I may add a lecture on that. But in general, if there's statistical stuff that you want to know about that you haven't seen yet, let me know and I'll cover it. Okay, but for today, analysis of covariance, that in general, a common theme of many of the methods in this class, if you have a response variable and then one or more predictor variables, and you want to know if there's a relationship between the response and the predictors, then depending on whether the predictor / response are continuous or categorical, you can choose different methods, and the choice of test that you use will depend on the type of predictor variable or variables. That if you have a single binary predictor variable, you can use a t-test. That if you want to know whether, like, case versus control predicts some continuous outcome, whatever that may be. On the other hand, if the predictor is quantitative, then you can use regression. And if there's a categorical predictor with 3 or more categories, then you can use one-way ANOVA. If you have several categorical predictors, then you can use multivariate ANOVA. Today will be considered a hybrid of analysis of variance and regression that's sometimes called analysis of covariance. It's basically if you have both quantitative and categorical predictors, and you want to say something like, sorry, I can tell I still haven't been sleeping enough, and you want to be able to answer the question, is the response variable related to these predictors? Oftentimes, the quantitative variable is a confounding variable that you want to control for. I actually had a question about this yesterday from a former student in this class, that she was trying to figure out if different types of chlorine solutions or some type of solutions are more effective as disinfectants than others, but she administered different concentrations of these disinfectants to each well in her assay. So this quantitative variable was sort of a confounding variable that she wanted to control for in this experiment, taking into account that regardless of which disinfectant you're using, the more cells will die if the concentration is higher. Are some disinfectants more effective than others? So I helped her fit an analysis of covariance model for that, and it was kind of a funky one, which is why she came to me for help. This class will only be doing simpler ones, but this is the basic idea. When you have both continuous and categorical variables, the predictor variables, and you want to see how they affect a continuous response, you can use analysis of covariance. So recall our ANOVA model looks like this, that if you have observation I belonging to group K, then the standard ANOVA model, the ith observation is equal to global mean plus the offset for group K plus noise, and the ANOVA null hypothesis is that all of these offsets are equal to 0. In other words, that the mean is the same for all the different groups. If at least one of the groups has a different mean, then one of the taus will be non-zero, and we would reject this null hypothesis. And in our two-way ANOVA model, it's the same idea, except that we have two different categorical variables. The examples we considered on Wednesday were agricultural examples that say you've divided your field into a number of different blocks, or if you're doing bench science work, maybe you have several different litters of mice. Within each block, you assign half to treatment and half to control. Then there would be two categorical variables, and you may want to answer the question of, are there differences from litter to litter, or the question of, are there differences between treatment and control, or are there any differences overall? In this case, the model would be observation I is equal to global mean plus the offset for whatever, for treatment versus control, plus a different offset for the block that you're in, and the null hypothesis is that everything's 0. Oh, an analysis of covariance model is, say that you have a quantitative variable that we'll call x1, a categorical variable x2, and that observation I belongs to group K in x2, then the analysis of covariance model is that yi is equal to b0 plus b1 times the ith iteration, the ith instance of x1 plus the offset for group K plus the noise term. Oh, it's just, as I said, kind of a hybrid regression slash ANOVA model. That the model is that there's a linear relationship between y and x1, but the relationship may change depending on what group x2 is in. In this particular version of the model, it's basically that the hypothesis is that depending on which group you're in, say the case group versus the control group, your regression line is just shifted up or down. You get a different intercept depending on which group you're in. Here in a few minutes, I'll show you a slight modification if you want to have different slopes between the various groups as well. And so the null hypothesis is the regression slope B1 and all of the taus are equal to 0. That is, that as x1 increases, there's no increase or decrease in y, and that the value of y also doesn't change across any of the categories for x2. And like in the two-way ANOVA case, we may also want to consider the null hypothesis that only the taus are equal to 0, or that only b1's equal to 0. And you can easily generalize this the case where you have multiple quantitative predictors or multiple categorical predictors or whatever. So, how do you fit an analysis of covariance model? Once again, the simplest way to think of this is just as a special case of regression. Create an appropriate set of dummy variables for each categorical variable, and then you fit a multivariate regression model to both the continuous variables and these dummy variables that you just created. Oh, an example of analysis of covariance. This is a data set that's built into R. That was an experiment to see if vitamin C affects the rate at which guinea pigs' teeth grow. That basically the guinea pigs were given vitamin C through two different delivery mechanisms, either by giving them orange juice or giving them ascorbic acid. The question is, does vitamin C affect the tooth growth of guinea pigs? And does it matter how the vitamin C is administered? Is it more efficient to do it via orange juice or via ascorbic acid? So, hopefully I kicked and screamed and preached about enough in the lecture a few weeks ago that if you want to see which variables are associated with an outcome in a multivariable model, the first thing you should do is look at the different variables one at a time. Just, I mean, it's probably not crucial when there's only two and one of them's categorical, but in general, it's still a good idea. Otherwise, multicollinearity can cause one to mask the effects of others, and you can get misleading results. So is there an association between tooth length and the dose? We said this data set's built into R. It's called tooth growth. So the model, we say length, twiddle, dose, and we see there's a very strong positive correlation between dose and tooth length. It appears that vitamin C does increase the tooth growth of guinea pigs. And is there an effect of the type of supplement? That is there a difference between ascorbic acid and orange juice? We can do that using a simple t-test, and it's not statistically significant at 0.05 is the bottom line. It looks like the mean is slightly higher for the orange juice group than in the ascorbic acid group, but we don't see a huge difference just based on this univariate analysis. We might think that there isn't actually a difference between the two. But let's look at this a little bit more closely to see if that's actually true. What if we do an analysis of covariance model including both dose and supplement? Well, something interesting happens. Now we get a fairly strong effect of both variables, that the ascorbic acid is associated with significantly lower tooth growth than orange juice. It looks like, so in this case, this is a dummy variable. VC stands for ascorbic acid. It took the orange juice group, or OJ, to be the baseline. So since this is a dummy variable, this tells us that basically we would expect that if no vitamin C were administered and you were in the orange juice group, which I guess is kind of an oxymoron, if you're getting no vitamin C, it doesn't matter which group you're in, but the estimate would be 9.2725 as the length of the teeth. As the dose increases, the expected length increases, and if they get it via ascorbic acid rather than orange juice, the expected tooth growth is about 3.7 less than it is in the orange juice group. And both of these X are quite strongly significant. I actually I mean, at some point I may have looked at the details of this data, but if I did, it was quite a while ago. The fact that when we do univariate analysis on the supplement type and it was not significant, but we get a strongly significant effect when it's included in the multivariable model, that may indicate that perhaps the sorbic acid group got higher doses overall than the orange juice group, and that artificially increases the values in the sorbic acid groups. If you just compare the raw values, you don't see that big of a difference, so it's kind of borderline statistically significant. But when you take into account the fact that the sorbic acid group got larger doses and still had lower tooth growth than the orange juice group, you conclude that the sorbic acid group has lower tooth growth overall. At least that's my guess. I mean, I haven't actually looked at the data to confirm this, so I could be totally off in left field, but that's probably the simplest explanation of this effect. And in general, if you have x1 that's continuous and x2 that's categorical, if you say LM y twiddle x1 plus x2, that'll fit an analysis of covariance model and automatically create the appropriate dummy variables. And note that if you include both variables in the model, you get a lower p-value for both variables, and I guess that's something I didn't point out on the other slide, that we got a stronger effect, that we got a stronger p-value not just for the supplement type, but also for the dose, which indicates that if you find the appropriate confounders and put them in your model, you can get better power. Once again, though, I mean, don't just mindlessly stick all your variables in the model, because if there's collinearity and you're not getting additional information from the variable, then you'll do worse rather than better. But if there really is some sort of confounding going on and you take that into account, then you can do better rather than worse. And you may be interested in other null hypotheses besides the simple one of are all the coefficients equal to 0. You may want to test the null hypothesis, the dummy variables for supplement are equal to 0, or that it would probably be all the dummy variables simultaneously. For the continuous variables, and I mean, you already have the p-value for that. And I mean, in this case, you don't even need to do anything fancy. For the categorical variables, there's only one of them. And so you just look at the p-value in the output for LM for that particular dummy variable, see if it's equal to 0. See if it's significantly different to 0, woohoo, we're done. But if the dummy variable has 3 or more levels, then we can't do that quite so easily. We may want to test the null hypothesis that all the dummy variables for a particular group are equal to 0. And you can do that once again by getting the ANOVA style output for the analysis of covariance model. The command to do that is the AOV command, analogous to what we did, analogous to when we did use the AOV command in the ANOVA case. It gives us, if you compare these p-values to what we saw in the previous slide, they're identical. The advantage to this AOV style output is that if there were 3 different types of supplements rather than 2, this supplement row would give you the p-value for testing the null hypothesis that both of the dummy variables are equal to 0, something that you can't get easily from the LM output. And in general, if you have y twiddle x1 plus x2, where x1 is quantitative, x2 is categorical, or you could have more x's in there, it will give you the same results as it would in the case of two-way ANOVA. It will test the null hypothesis that all the dummy variables for a particular predictor are equal to 0 simultaneously, and yeah, I think that's pretty much everything I had to say about that. And when you're doing analysis of covariance, you may also want to consider interactions that in this I really need to sleep more. That in the tooth growth example, that maybe the slope is different if you're in the ascorbic acid group than if you're slope may be different if you're in the ascorbic acid group than if it is in the orange juice group, and the model we've considered thus far, it assumes that only the intercept changes from group to group. That, in other words, the increase in tooth growth for a corresponding increase in the dose of vitamin C is the same regardless of how the vitamin C is delivered. The only difference is that your growth will be about 3.7 units on higher if you're in the orange juice group than if you're in the ascorbic acid group. And that assumption may or may not be true. It's possible that if you're in the orange juice group, a given increase in the amount of vitamin C leads to an even larger increase in tooth growth than you would have gotten if you were in the ascorbic acid group. And you can test that hypothesis by looking for an interaction between these two variables. So, the analysis of covariance model with interactions, once again, let's assume we have a quantitative variable x1, categorical variable x2, and that observation I belongs to group K in x2. So if we include interactions, the analysis of covariance model would be B0 plus B1. Note that rather than just saying B1, it's B1 sub K times X1 plus tau K. Basically what that's saying is that depending on which group you're in with respect to the categorical variable, in the tooth growth example, depending on whether you're in the ascorbic acid or the orange juice group, the slope is different. So you're just fitting a different slope for each group in X2. How do you fit an analysis of covariance model with interactions? Well, you need to define your dummy variables a little bit differently. First of all, you define a second dummy variable that's not actually a dummy variable. We just call it zki, which is basically equal to x1. That is, it's equal to the continuous predictor if you're in group K, and 0 otherwise. So in the tooth growth example, we define a z that says if we treat the orange juice group as the baseline, we define the second dummy variable that's equal to the dose, or shouldn't call it a dummy variable. We define this new variable called z that's equal to the dose if you're in the ascorbic acid group, but if you're in the orange group, it's equal to 0. And we'll also define dummy variables for orange juice versus ascorbic acid in the usual 0-1 manner. So we fit a regression model to both the dummy variable for the supplement type and also these zk's defined above, in addition to the original x1s. And that will that will effectively give you a regression model with a different slope depending on which group you're in. If you didn't follow that, don't worry about it too much. R will do this for us automatically, but I just felt like I should give at least some explanation of this. So, and yeah, basically, I guess we just said this, and yeah, anyway. So before you just mindlessly start throwing interactions into your model, it's oftentimes a good idea to look at the graphs to see if we see visual evidence of interaction. You can do that with the interaction.plot command in R. In this case, we say interaction plot. We say plot tooth length versus dose for separately for each value of the supplement. We'll get one line for orange juice, one line for ascorbic acid. If there's no interactions, we would expect these lines to be approximately parallel to one another. And yeah, in general, if you say interaction.plot x1, x2, y, that will plot y versus x1 for all the different values of x2. This works if x1's numeric, but the way it's plotted, it basically converts it to a factor before it does the plotting. So in this particular case, the interaction plot looks something like this. For the ascorbic acid group, it does look quite linear, but for the orange juice group, well, there's kind of an interesting shape in this graph. It looks like it's sort of piecewise linear. I mean, I don't know how many different dose values were here, but one way or another, it looks like these lines are not parallel, that for high values of orange juice, the slope is less than it is for low values. So, assuming that the slope's the same for both the ascorbic acid and orange juice groups probably isn't terrible, but we might get a slightly better fit if we fit a different slope to the ascorbic acid group. And so the simplest way to do that in R is to just tell it to fit an interaction. R will automatically create all the appropriate dummy variables for us. Recall this notation in R. If you say length twiddle dose star supplement rather than dose plus supplement, that says include the two main effects of dose and supplement, but also include an interaction between the two. And in this case, I mean, the interaction isn't huge, but it's statistically significant. It's interesting to note that the effect of supplement becomes even stronger once we model this interaction correctly. It's actually semi-remarkable when we just mindlessly compared the two groups using a t-test without considering the effect of dose at all. It wasn't even statistically significant. Now we're getting a p-value of 0.0005. When you take into account the confounding variables here, you can detect associations that you wouldn't have had power to detect otherwise. So what this seems to be telling us is consistent with what we saw in the plot, that there's some evidence of a slightly different slope for the ascorbic acid group than for the orange juice group. It isn't huge, but it is statistically significant. If you really wanted to be a perfectionist about this, it looks like it may not be that the orange juice group has a different slope, but it isn't precisely linear at all. So we might try to fit some type of nonlinear model to that, but that's not really something that I cover in this class, other than maybe I will give one quick lecture on how to do this in the context of LD50 curves if the toxicology students in the class are interested. But yeah, that's the basic story there. In general, if you say y twiddle x1 star x2, that'll fit an analysis of covariance model that includes all possible interactions and will automatically create any needed dummy variables. And if you ever want to include a specific interaction term manually, you can just say x1 colon x2, and that will fit an interaction without any main effects. In general, it's usually a bad idea to fit an interaction model without including main effects, but there are some situations where you may want to do it. And the interpretation of this R output is you get a slightly different slope for each group. I guess I should have talked about this on the other slide. This is what this is telling us is orange juice group is the baseline. So in the orange juice group, the slope is about 7.8. But if you're in the ascorbic acid group, the slope is 7.8 plus 3.9. Likewise, the intercept in the orange juice group is about 11.55, but the intercept in the ascorbic acid group would be 11.55 minus 8.255 is how you would interpret that output. So, just final notes, I talked about this a bit earlier, but as we improved our model, our power to detect the supplement effect increased quite drastically. When we didn't consider the confounding effect of dose at all, our p-value wasn't even statistically significant. When we include dose, suddenly we got a p-value of 0.001, and when we include the interaction, suddenly it goes from 0.0005. So I mean, our p-value dropped, what is that, something like 1,000-fold when we included the appropriate confounders. So identifying and controlling for the appropriate confounding variables when you do regression is a very good idea. And so things to remember for today is you can use analysis of covariance to study the relationship between a response variable and both quantitative and categorical predictors, and make sure you include all the relevant predictors in your model and you'll get better power. Any questions about anything today? Okay, well, reminder to the one person in the room, homework 5's due next week, and we'll try to get homework 6 done over the weekend. That'll be the last assignment. Other than that, it's just basically a take-home final in the grant writing project for those who choose to do it.